The iodine in the sand can just be flushed down the sink. Got our little miniature dustpan and brush for wiping up little spills like that. Little stand down the sink never hurt anyone. So you want the hot plate to be hot enough that when you stick your hand, an inch or so above it, it's a little uncomfortably hot. Crank that up to close to 70. It's getting there, but it's not really quite hot enough yet. So the way the phospholipid acid stain works, it's an oxidizing agent. So things that have alcohols in them, especially if it's not a tertiary alcohol, if it's primary or secondary alcohol, should stain nicely with phospholipid acid. We would expect the 2-phenylethyl alcohol to stain very well. You want to dip the plate in fairly quickly so that it goes all the way above the spots, or pretty much up to the solvent front, and then let as much of the solvent as possible drain off. And then we'll set that there so we can dry the back of it. And dip the next one. Drain as much solvent as possible back into the jar. And then I want to put the cap back on so I don't knock it over. Because if you knock this over, it's a big pain in the ass to clean it up. That's known as doing the Colby, after the student who dumped the entire contents of a jar once in the hood. I'm going to take my gloves off before I heat those because I don't want to melt the glove to the hot plate. I've done that before and it hurts. So I want to dry those off, let as much of the solvent disappear as possible, the ethanol. And then I want to heat that. It's usually best to heat it with the silica side towards the hot plate. What we're expecting is blue spots for alcohols, ketones, aldehydes, things like that. Sometimes show up as more like orange or tan spots, sometimes kind of greenish. And then the background is going to be kind of a pale green. So sometimes I rest the forceps on the hot plate. I need to be careful not to touch the plate itself to the hot plate, but I want to kind of heat that. And if it gets too hot, the plate will start to curl because the plastic will start to soften. And if that happens, I'm going to flip it the other way up so that I get a kind of curl back. If you touch the plastic to the hot plate, it will melt, and that will give lousy results. So you can see that the eugenol is staining quite nicely, the dark blue. The guaiacol is staining, but not staining as well. The stain there is probably the extra pi bond that's staining, and then the vanillin is staining, but a different color. Right? The vanillin, the aldehyde, is actually staining more of the orange color that I was talking about. You don't know exactly how long to leave it, but you kind of see it like that. And you can see that there's a little bit of tail on the spots. So that looks decent. It actually almost looks as if it developed sideways, and the vanillin went that way, and the eugenol went kind of that way, and then the guaiacol would have gone all the way off the edge of the plate. I'm not 100% confident of this plate because of that. There could be an impurity in the vanillin. But it is consistent with the UV activity of the other plate where the eugenol and the glycol moved about the same distance. So I'm definitely expecting the 2-phenylethanol to stain nicely because it's primary alcohol. I'm hoping the linalool will because of the 2 pi bonds that are in there. One of them is a vinyl group, just like the vinyl group that's present in the eugenol. So we would expect similar behavior. The 2-phenethyl acetate will probably not stain. Esters are very difficult to see on TLC unless they're UV active because they just don't stain very well. You can see the plate's curling a little bit because of the heat, so I'm going to lift that up a little bit. It's easy to heat them too much. So set that aside. I'm going to turn that down a little bit because it has now gotten quite warm. So you can see that in the phosphomolymptic acid, the linalool stained kind of a dark blue, the 2-phenylethanol stained kind of orange, but not very strongly, and then the 2-phenylethyl acetate virtually didn't stain at all, maybe a little bit of an orangey brown. You can see the linalool is obviously a little impure. There are some other spots in there that are lower RF. And then our eugenol stained really well. Our vanillin stained quite nicely, but a different color, so we can tell the difference between them by color. And then our glycol stained, but not as strongly as the eugenol. So right now we still don't have a very good way of distinguishing glycol from eugenol because they have a very similar RF in both the solvent mixtures, and they have similar staining behavior as well. What we hope is that by a combination of staining behavior in these 2 stains and RF values, we can get something that's going to separate all of them. So the linalool has a very similar RF to the glycol and the eugenol, but maybe if we move into a different solvent mixture, we can change that situation. The 2-phenethyl acetate obviously has the higher RF, and we can afford to go to a slightly more polar mixture because it's still not moving all the way to the top, and maybe a slightly more polar mixture will help us separate the other things. The 2-phenylethanol and the vanillin have distinctly different RFs. Easier to see the difference in the 2 to 8, the 20% ethyl acetate than it is in the 10% ethyl acetate. So you'd reach the conclusion that this 10% ethyl acetate hexane mixture isn't really polar enough for this particular set of compounds. The 2 to 8 is better, but by going up to 3 to 7 and running another set of plates, we might get even better RF separation. So I'm going to turn the camera off. I'm going to make up some 3 to 7 mixture and fill some chambers with that, and then we'll come and run some more plates.